and welcome to yet another session of Cycle 25. This time we're lucky enough to have JR with us, and we are going to be talking about 3D printing for ham radio. I got a sneak peek at... Welcome to yet another session of Cycle 25.
All right. So can everybody see my my screen? Just want to make sure.
Yep.
All right, awesome. So good morning, everybody. I'm JR, N7JRJ. I'll give you a little background. So as we were talking about, in various Cycle 25 sessions about, some of us that were doing 3D printing, it got me thinking back to my own start with 3D printing, which really I owe to my son, right? So my son came home freshman year of high school. He had a figurine. He's like, "Dad, this is really cool. It's a thing that I printed with my 3D printer." And I went, what's a 3D printer? And did a Google, right? And my son's next request, of course, was to get a 3D printer. So we did a little bit of searching. I had my son do some chores over the fall, and in Christmas, a monoprice printer showed up under the tree. And for a while, we did a lot of printing together and learned kind of the traps of what it was like to go from having an idea for something. And as you can imagine, 14, 15-year-old kid, his idea was to build lots of ray guns and Star Wars things and that sort of stuff, which was cool at the time. But I began to see the utility of this to do other sorts of utility things. So this really describes my journey in 3D printing. I realize in the group today, we have a number of folks who are active 3D printers. So I tend want to be kind of the conductor more than kind of the sole participant. So I'll be looking for hands up on comments, feedback, what have you. The other thing about this morning is, as Rod said in the introduction for this session, is I'm going to do some demos because I don't know how you talk about 3D printing by just having static PowerPoint slides. So I'm going to increase the risk factor of this presentation by trying to do some live demos. I've got some records in the background if we need them. But Rod, I'm going live. So
and standard disclosures apply, and
you'll
the exemptions, all that good stuff. You're a brave man, JR.
All right, I appreciate that. Thank you. So, as we think about 3D printing, so again, as I was coming up to speed on 3D printing, I Googled a lot of resources, looked on YouTube at the time, and most of the resources that you could find were about specific topics, a printer, materials, that kind of stuff. And so what it really took me time to figure out was what I would describe as the workflow associated with 3D printing, right? So the focus of this presentation is going to be more about how do you get from an idea for a part, I need to make something like this, to actually getting it printed and having it be useful, having it actually be, something that we can, apply in various formats. So this is going to really drill down on the steps that I see are kind of the key steps. And it looks something like this, right? So we'll start with a discussion about the design process, how you think up these ideas, where you find them. Then we'll go to a key step in printing, which is slicing, and that's really converting from a design form to a printed form. Then we'll focus on printing itself, and then I'll finally give a few comments about finishing. But we'll spend the majority of the time really kind of talking about some of the key activities that lead to a print. So does that sound good to everybody? Any questions before I get moving? Cool. So let's start with design, right? So there are kind of three ways to think about the design process, right? You can use an existing design. You can code a design, which for me as a software developer was a major find, right? Early in my experience was to discover that there's a rich set of programming supports for a design of parts, or you can visually model a design. And if we use an existing design, one of the resources that I really have gravitated to is this site called Thingiverse. So I thought I'd show off Thingiverse because I think, again, if you're entering 3D printing, the hardest part is also, the hardest part of this is knowing where to start. And I feel like Thingiverse is a great place to start. So let me kind of show you Thingiverse. For those of us who use Thingiverse, Thingiverse can be a little bit frustrating at times, but because its growth, I think, is outstripped the capacity of its of Ultimaker to really support some of the usability factors. But it is amazing if you're looking for parts. You know, this is Thingiverse. There are literally thousands of 3D designs of parts that you can make in Thingiverse, and they're a rich collection of ham-related parts. So this happens to be some things that I've collected over time. I'm sad to report that I have made most of these things, but Thingiverse has a rich number and amount of 3D parts for specifically for things around ham radio or electronics enclosures and things like that, right? So things like this PCB enclosure is a great example of something that you can find on Thingiverse. It has a quality known as being parametric. So you can actually download the open SCAD for this part to vary the part to move the PCB hanger points around or alter the geometry of the PCB of the enclosure itself, which really is convenient, right? It's less about having to be in a design tool and make those decisions yourself, more about being able to kind of grab something, kind of quickly make use of it either directly or use OpenSCAD. Sorry, was there a question?
Yeah, JR, I'm just going to ask you one thing. Your audio, is there a microphone close to you or could be closer?
Is.
Ah, okay. Okay, well, we'll do what we can. It's all good.
Okay. Yeah, and by the way, also a new creator, so more of a maker than a creator. So I'm learning I need those
it's all
things
good.
like microphones. So, but I'll make sure I speak up. So so again, Thingiverse is a great resource. As you can see, when you're looking for parts in Thingiverse, what you're really looking for are these things called STL files. And I'll talk a little bit more about what an STL file is, but that's really the entry point from, or kind of the exit point of design and the entry point into slicing. So with that as kind of background, let me click through that. Let me show you an example of what it's like to write code. Now, I said earlier, I'm a software developer by experience and background. So I quickly gravitated to kind of the de facto design environment, I think, for 3D printing. You'll find a lot of open SCAD parts in Thingiverse, for example, that you can download and modify. Open SCAD, while it's not a perfect programming environment, as you'll see when I demonstrate it provides a lot of the common components that you would want to use to make a part. So I'll show you a really simple part just to kind of demonstrate how you can start. So this is actually a part that I made that's just a kind of an easy little shack spacer. I wanted a device to kind of lean up so I could see it better in the shack. And you can see that to make this part, I'm using some utilities within OpenSCAD, but it really is just a few lines of code. So kind of explaining OpenSCAD, you can see that there's the visual view of the 3D part that you're working on the right here. There's the code on the left, which is a pretty classic kind of scripting style language. It has some block-based constructs, so you can have functions and subroutines, but a pretty simple language to approach. Again, the value of this sort of a thing is that if, let's say, I want to change the width of this part, I can change it to be 160 millimeters in this case. And you can see the part immediately changes. Now, this is the preview view of a part to actually make it into something that can become an STL file, which is that important file type, kind of exchange file type. We first need to render that part. And that'll do all of the work of taking that general 3D design and turning it into a mesh, which we'll describe in a second. And then once it's a mesh, I can export it as an STL file and then take it into the slicing process. That's a pretty simple example of OpenSCAD. It can get pretty complicated. I'll show you quickly. Just this is a a 3D enclosure for a Raspberry Pi 4 that I modified. I wanted to put a fan on the Raspberry Pi 4 case. So I downloaded this example from Thingiverse. What's kind of cool about this is that you can do things like I can, right now I'm showing the whole part. I can just show the base of the part and then preview that. And now I've taken away the front part and you can see the outline of the Pi 4 there. I can take the Pi 4 out. And now that's something that's ready to be rendered and then sent to a printer, right? So a lot of power in OpenSCAD. Just wanted to show that out. Now, I will also demonstrate my weaknesses here by having just a single slide on CAD design. So my strength is things like software development. You know, we might describe my weakness as some of the modeling approaches to developing parts of a similar type. But there are a variety of different tools, a diverse spectrum of products. You can start from very simple products like Tinkercad, which are literally 3D CAD design through a web browser, to Autodesk Fusion 360, which is a hobbyist we can get for free. And it gives you a lot of power in the design process. Obviously, something like Fusion 360 is cool to folks like hams because we can also do PC board design using 360. So it gives you the same utility for the tool, can serve multiple purposes. All right, so let's talk a little bit about STL files. STL, standard tessellation language, or standard triangulation language. And this is the grandfather of 3D printing interchange formats. And what it does is it describes a part, like this 3D part, as a series of triangles. And you can see in this little diagram kind of the triangle forms that are the surface of the part that you're then going to print, right? And it's kind of important to understand this in the sense that when we take this design in its STL form, or its 3MF is another newer format, what we're really going to do when we slice is we're going to take horizontal chunks of this, and that's what the printer is going to print, right? So a lot of the complexities and the things that we have to pay attention to in 3D printing are the interaction between this kind of 3D design and the way we're going to print something with a 3D printer. So you can see that there are horizontal areas in this particular print, and I'll show you kind of how we overcome this in a few minutes. These horizontal areas, 3D printer, think about that 3D hot end moving. As it's moving horizontally, if there were no support underneath this, we would see something called stringing, as this handy example shows, right? So I'm sure if you've been around 3D printing, you've seen something that looks like this, I'm sure, at least if you're average like me, right? So there's some complexities here that we'll talk about when we get to slicing, that slicing really solves for us. So any questions? Just want to make sure I'm looking for feedback. All right, so let's turn to slicing. And this is kind of an overlooked process. I didn't really appreciate when I started 3D printing kind of the importance of slicing until I got into situations that looked like this, right? And then I started really kind of diving into slicers themselves to understand. And most of the common slicers that are out there try to hide some of that complexity, but you can definitely expose it for more complicated things that you might be working on. But again, each layer that we're producing as we move from this STL format to the 3D printed format is called a slice. The slicer takes into account the material that we're using. So if we're using PLA or ABS, as well as the volume of the print bed that you're printing against. And so the output of the slicing process is something called G-code. Those are the explicit instructions that are getting sent to a 3D printer. So these aren't just compilers. Slicers have a really key role in the process. You can modify parts. I'll show that when I demo slicers. They can also allow you to, They also allow you to modify aspects of the print itself. So if you have something called stringing, which are little strings that can appear in a 3D print, you can actually either vary the temperature of the hot end to deal with that, or other aspects of the printing process to deal with those kinds of artifacts. So again, slicers are important. There are two predominant slicers. The one that I'll demonstrate today is Prusa's Prusa slicer. The other is Ultimaker Cura. Most 3D printer manufacturers will bundle a slicer, sometimes white labeled. One of these two are an open source equivalent. I've actually used Cura with my Prusa printer. We'll describe that later, so you can mix and match slicers as you will. So again, demo rules are going to apply here, but I'm going to bring up a slicer. So this is Prusa slicer, and this is that part that I've been holding in my hand. Let me kind of point out some of the aspects of this. So the first thing that you'll see is this STL part on the print bed of the Prusa printer. If I were to change, and you can see on the right-hand side of the slicer here, I'm assigning a quality to the print, and that really has to do with how thick a layer is. I'm assigning the material that I'll use to print, and I'm also assigning the printer. Now, if I had a Creality Ender 3, I could change that here, and now the base of the printer shows like it's a Creality Ender 3. If I were to hit slice, the G code that would be sent would be appropriate for a Creality Ender 3. So again, slicers are a utility app that you can use one application and actually address multiple printers. So within slicing itself, let me kind of show some of the activities that you can do with the slicer. So as I pointed out here, we have we're setting up a print at 20% 0.2 millimeter slice widths using PLA, using my Prusa printer, and with an infill of 25%. Now, infill is what happens inside a particular set of layer of the print. So in most cases, you're not printing solid, right? You're not printing every printable millimeter of a particular part. So in the interior sections, the slicer will determine the way to fill those with something called infill that allows you to use less filament, but gives the part strength, right? And we'll illustrate that as we do a slice here, kind of how that works. But in this particular case, if I were then now to slice, you can see that I have turned on supports, and these supports are removable pieces of the print, right? So I print this device. The device will look like this when I'm done, but the slicer lays down this filament in a way that it can be easily removed, and what will be left is the printed part, and the printed part without nasty issues at the top in this particular case, right? Now, one of the cool things you can do with a slicer is you can look at each of the slices, right? So this is an example of kind of peeling back the layers of the slice so that you can see how each layer is being deposited. We'll get down to this base, because in the base, we'll begin to see what that infill looks like, right? So that's an infill of 25%. If I were to increase infill here to 30% and reslice, you'll notice that infill changes, right? So now we're putting more material into the part, making the part potentially a little bit stronger, right? Or adding some mechanical property to the part, and doing that selectively. Now, on the right side is as you're slicing, one of the things to point out here is that you can get information about how much material, how much filament you're using, right? So in this particular case, I'm using about 6.92 meters of filament. You can actually put a cost to these, and so the cost is 62 cents to build that part. And also, most importantly for me at least, the amount of time it takes to print the part, right? So again, if we zoom out on this a little bit, I'll show you one other thing before I send this part to the printer, talk about live demo rules. And let's say I kind of like this part, but I've done some measurements and I've downloaded this from Thingiverse, and I've determined that I need a little bit more width in the part, right? So I can actually use the slicer to vary the geometry of this. So, maybe it says 86 millimeters, let's go to 90 millimeters in the z-axis, right? So I can change the definition of the part, and this is something that I've used a lot in slicing. Like there's something that's almost right, not 100% right. So I use the slicer to kind of vary the dimensions before I send it to the printer. So again, let me slice this part and then illustrate then what you do with it next, right? So the end game of a slicing operation is the generation of G code that is then sent to the printer. Now there's two ways to do this. The classic way is that you download this to a SD card, take the SD card over to your printer, right? The better way to do this, I think, is to use a utility. And again, in printers like Prusa, Creality, Monoprice, others, typically there's a USB interface that one can use to connect to the printer. There's also a Raspberry Pi application that you can use to send G code to a printer called Octoprint, and I'll demonstrate Octoprint. But what I'd like to do first is send this to my Octoprint printer. And then you may hear in the background, my printer will heat up and we'll then start printing that print. We'll look at it a little bit later in the presentation. So that's slicing. Again, there's a lot of knobs and dials. Actually, let me go back to my little, to my slicer here. Just to point out that while this interface looks pretty simple, there is an expert mode. You can get into deep parameters in the printer, filament settings, print settings, and this is where the brave tread, right? Because you can both fix things and cause problems by tweaking these variables if you're not really deeply schooled and kind of the impact of those things. So I'll just provide that as a warning. And again, in most cases, using Prusa, something like Prusa Slicer or Cura out of the box without doing a lot of tweaking, especially if you're using a known printer and known filaments, is pretty easy, straightforward to do. Okay. So we talked a little bit, or I showed a little bit about slicer supports. And again, these are temporary additions to models, right? They allow the model to print. So this is an example of a IC 705 case that I printed that required that look of slicing. You can see in the picture that I've snapshotted that there was a series of, I printed it this direction, and there were a series of supports underneath to support some of the complex angles of that part, right? But all those pieces come away after you're done printing, and you got a nice case that cost you $4 in materials. And that's kind of what it looks like, kind of as an illustration. All right, so to finish up this section, let's talk a little bit about G-code files. And again, G-code language is derived from CNC applications. So if you're around CNC, then G-code is going to look very familiar to you. G-code adds some commands to classic CNC that have to do with the temperature of the hot end and the amount of material that you're extruding or even pulling back in the case of 3D printing. There are cases where you actually want to pull material back in before you move the hot end so that you don't get strained, for example. And so G-code is kind of the lingua franca of most 3D printers. It's the equivalent of assembly code, and we can actually monitor with utilities like Octoprint the transmission of G-code if we think we're having problems with interactions with the printer. Okay, so now let's talk about the action end of the equation, right? So printing, there are a lot of variables to deal with. There are filaments, there are layers and getting a print started. And then there are things to be concerned about having to do with build volume and the kind of materials and kind of the interaction between building a larger part that looks like this with a standard printer. It takes a little bit more work. So, a little bit about printers. There are a number of 3D printing techniques. Two are commonly used in hobbyist printing. The older kind of original format, if you will, of 3D printing is stereolithography. It's resin-based. SLA parts print top down, which is really interesting to see if you've never seen it. But the format that we use most is fused deposition modeling, or FDM printing, and you'll see that initialed a lot, FDM printing, blah, 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 right? The FDM techniques were popularized really thanks to this movement that occurred in the late 90s called the RepRap movement, which was really about building self-replicating devices using 3D printers. So the core of RepRap was you ought to be able to build a 3D printer using a 3D printer. A lot of companies that we know, like Prusa, were started from that movement. A lot of the reason that we have cheap 3D printing today is because the original patents that were applied for in the 80s were falling off in the early 2000s, and so that allowed the RepRap movement to move and incorporate into open source designs a lot of this previously protected technique. There are still areas where patents apply, so you will see, for example, Prusa, which is the printer that I own, will show you the design for an enclosure, but it won't make an enclosure or make a printer with an enclosure because supposedly it conflicts with an existing and still enforced patent. So there's still some areas where I think there are improvements to be made here in the practice, but again, just a little bit of trivia on that space. So I thought for fun, I would try to correlate 3D printers with types of radios, just to give you a sense of at least this is JR's impression of 3D printing related to ham radio, because this is about ham radio, right? And so I'd put my first printers, monoprices. I actually burned through two of them, actually had power supply failures from, I guess, overuse. I would compare that to some of the cheaper copied Chinese radios, maybe the Xiegu G90, because they primarily copy open source designs. They're not providing a lot of innovation. We might step up on the Xiegu 6100 because it's a more innovative design, much like the Creality 3D Ender, right? So Creality, Taiwanese maker, I think Taiwanese or Chinese maker, but they're adding some new innovations in the work that they're doing. They're actually contributing more to pressing RepRap techniques in FDM printing. Moving up a bit, and I know this is a popular printer for multiple of us on this call, I would describe my Prusa printer, which I built from a kit, a lot like building an Elecraft K3 from a kit, both really known for just engineering solidity, right? So highest quality, long lasting, again, kind of in that comparison. And then I compare the Flex Signature to something like a Dremel Digilab. So I don't know if you're familiar with the Dremel Digilab, but a lot like Flex, there are no USB devices in use here in default, right? You're using an Ethernet connection or Wi-Fi, and they really are a drop in place and use printer, unlike something like a Prusa printer or Creality or Monoprice, for example, where you have to do some fiddling to get the print right. A Dremel, you drop it down. Now, there's some trade-offs to that. There are not quite as many knobs and dials as there are on a Prusa printer, some limitation in materials, but overall a good experience, and at the same price point as a Flex Signature radio. So you can get the 6400 version of a Dremel Digilab, you can get the 6600 version of a Dremel Digilab, you can go to your heart's content, right? And then if you're into contesting and looking at high-end hardcore contesting radios, then you're really looking at 3D printers like Ultimakers and that sort of thing. So I'll pause here. Any thoughts or feedback on that?
Boy, JR, you know how to start an argument in the ham radio community.
I think, JR, what you've done is awesome.
I think it's great.
It is, JR, but could you talk about, do you need to ground your 3D printer?
Exactly.
You need to use a balance.
Hey, I have applied toroids to my 3D printer. I will say that for sure.
So, Jim, this is actually a really neat design and that you're showing here. I think, you know, I get a lot of questions, which printer should I buy? And, you know, to answer that, you really need to know something about the personality and experience of the person involved. And that's where it's maybe a little bit different than 3D, than ham radio. Because I mean, all of these rigs will work. They just differ in quality, but you can still use them. Whereas somebody who really has no sense of how to fiddle or any of the theory or anything like that, if they buy a cheap clone and they have to get it working properly, that can be a sort of a dead end for them. And, you know, I think that's one reason why the Prusa is so popular, because it gives you a reasonably priced printer that's not quite plug and play, but it's so darn close the average person can just make it work. And so I think you need to know something about the personality and skills of the person to get them started, because I've seen a lot of people and heard from a lot of people who've just dead-ended trying to go to the cheap route and just never get it working and give up.
Yeah, absolutely. And again, I think you know, there's a pay me now, pay me later sort of quality to this, right? And it's interesting. I've read reviews, kind of, you know, the classic magazine reviews, kind of like the PC Mag article that I excerpted here, they'll describe Prusa printers as fiddly, but I've never fiddled with my Prusa printer, right? So
They are not fiddly.
John, I would expect you to say that. But again, that's sometimes an impression of these things, which could push someone away unnecessarily, right? Because we all know
it's a great analogy you got there with the videos, and as well, I appreciate the comments that you for programming your prints. I have a software development background as well, and I didn't know that was really an option. So that really piques my interest for the whole hobby as well. So thanks for that.
Cool. Awesome. All right, so let me move on from here then. So again, I just wanted to collect, because that's you're right, Rod. That was to create a controversy, right?
JR, can I ask a quick question before you move forward?
Yeah, please. Yeah.
So when you're trying to think about strength, you talked about infill. What's your opinion on trading off increasing infill versus increasing the thickness of the walls, the outer walls?
Yeah. So it's a combination of tweaking there, right? I've tended not to mess with walls unless it was a part that I thought was going to get some wear, right?
Yeah.
And then really focus on infill. But actually, let's talk about filaments, right? Because the filament that you use has a lot to do with the decisions you make there, right? And so, you know, again, filaments are the key ingredient, but what I thought I'd do here is kind of describe what I think are really good starter filaments for various reasons, and then talk about some more advanced filaments, right? So the starter filament, right? PLA, it's very easy to print, doesn't require a heat bed for most kinds of prints. It has a wide variety, a pretty wide temperature tolerance. It's very inexpensive. It's biodegradable. You know, we can maybe eat this. I don't know. It's biodegradable. And so I tend to use PLA for most of my enclosures, shack parts, things that I don't expect to be outside and that aren't going to get a lot of mechanical stress, right? So PLA is really good for that. As soon as I start talking about parts that are going to get some form of stress, then I'm going to move to something else. PETG is kind of the next level of progression. I think it's very easy to print. It does require a hotbed, a heated bed. PETG by background is it's the most widely used form of plastic, right? Thermoplastic. Unfortunately, it's filling up our oceans. So there's, plus minus to this, but again, it also has much better mechanical qualities for shock absorption and that sort of thing. And then if you need what we might describe as a hard part, right? So this is a part that we'll use in something like this clamp, right? That clamp, which you might use on your workbench, on your woodworking bench, you want to be strong and be able to take a lot of, impact and torsional sorts of things. And that's where, Pat, to answer your question, I built this with thicker walls and with more infill. Now I've read on the inner tubes and intend to follow this, that infills greater than about 40% really don't add a lot of value. So I tend to max my infill at 30 to 40% for the parts that I'm building that require that sort of strength. But again, it's the interplay between the type of material and the application that you're trying to make with the part. One of the things I'll point out, both Cura and Prusa Slicer allow you to vary the geometry of the infill, right? So there are certain, again, if you do some deep reading on Prusa's site, you will find reference articles, I can dig them up if you're interested, that will describe the benefits of kind of the plus minus of different types of infills. So certain infills have better strength, but make the part more bitter or brittle. Other infills are great for giving some give to the part, which you might want in certain kinds of impact resistance that you're looking for, that sort of thing. So, so lots of variables here, obviously. The more advanced filament options. So TPU is one that I've used. It's great. It's the soft, bendy plastic. It's actually very easy to print. You have to be a little bit careful about the type of TPU. There are multiple formulations of TPU you can use, but I've actually used that to build cases for my HD, right? Build a case, TPU, pretty easy to do. You have to pay attention when you're done using TPU to clean out the printer hot end, because some remnants of filament in the hot end can cause problems later print. I've never actually experienced that, but I have always kind of followed that as a best practice. The next material that I'll point out as a interesting material that requires a little bit more care is something called ASA. It's a cousin to ABS, but with better UV properties. So I use ASA now for all of my outdoor parts. So some of you may know, I found my way into this group thanks to an interaction that I had with John Fallow through Thingiverse, because I was printing some parts for my LZ1AQ receive antenna. And the parts from John that I ended up printing, I printed with ASA, and I expect it to have a long life. So it's really a superior material to ABS. I think if you can print ABS, you can print this material. And then the final material, which is kind of my aspiration, I'm not there yet, is any sort of polycarbonate. These are the ultimate in terms of material strengths. They're also very expensive and hard to print. So you can literally melt the plastics around your hot end that are holding your hot end in place because of the temperatures that are required to print this. So I just point that out as you can definitely do it as an amateur. It's considered more of a pro material, but man, I've been fascinated to print with that stuff. So, okay. So again, diving a little bit into layers here, right? So we've covered materials. And again, any questions on materials? Sorry, I don't mean to rush that topic because I think it's important. Okay. So diving into layers then, there are things that we have to do, making sure that the print bed is level, making sure that relative to the part that's being created, that Z is accurate across all of the axes of the printer. That can definitely, with the less expensive printers, be some work, right? My monoprice, I literally spent 6 months trying to get the leveling right on the printer, so that I could get a level printing process. The strength of the print depends on the adhesion between layers, because remember, what we're doing as we're building this print is we're laying down successive layers of this thermoplastic. And so adhesion is important. Some of the early outdoor parts that I built for an antenna actually broke apart because the adhesion was not solid, and it was before I really understood about the need of an enclosure for plastics like ABS, which I'll talk about in a second here. But getting that adhesion requires that not only you have the right temperature at the hot end, but also you have the right ambient temperature around the part. And again, in materials like ABS, like ASA, it's very possible to get warping because the plastics will begin to shrink as they cool, and also to have layers kind of come apart, which obviously isn't great for strength or usage of the part. Again, my general advice is accept the defaults of the slicer if you're using no materials, unless you kind of know what you're doing there. Again, the bigger the part that you're creating, like this one, the more likely it is that the part will deform as you're printing it. And again, smaller parts can still have problems with adhesion between layers, and this effect becomes critical in those materials that I described. In all cases, getting that temperature right around the printer is better. So the question is, how do you address that? And the answer is an enclosure. So this is an example of the enclosure around my Prusa printer. This enclosure was actually described as a lac enclosure. It actually uses 2 IKEA lac tables, which you can get for $9 or $10 at IKEA. So that plus some plastic around, probably $50-$60 in a weekend afternoon to build it, and you've got a really nice, beautiful, serviceable enclosure. Once you have an enclosure, the value of that is that now you can manage the temperature very carefully, monitor the temperature very carefully for parts that you think are intricate. It's absolutely critical with either larger prints in ABS or almost anything in ASA. Okay, so let me finally kind of talk about the print server. So I talked about the print server a little bit earlier in our conversation, and this is really something that, while it's not required, you can definitely, when you slice a print, drop it on an SD card, take it over to your printer. It's really a nice utility to be able to use something like Octoprint. So this is kind of a diagram. Octoprint is a print server that lives on a Raspberry Pi. It's connected to your printer. My version of Octoprint also has a camera connected to it. And so when you are printing a part, and I'm going to use the CAN demo this time because, true to demo rules, my printer has not started. But this is kind of an example of Octoprint in action. So this is another part that I was printing earlier. You can see I get a camera view of the print as it's proceeding. You can see that on the left-hand side, we have the status for the print. So it's giving me how far through the print I am, how much time there is, and it literally can show you layer by layer the print as it's proceeding, right? So as we flip, I'm going to pretend to flip tabs here to show off different parts. So this is a view of Octoprint that shows you the hot end temp and the bed temperature for your printer, right? So monitoring that so you can kind of stay attuned to that. And then this is a view, the G-code viewer, that's actually showing the G-code as it's being laid down on the print, right? And you can actually zoom in and zoom out on this. You can see where the extruder is being retracted or extended. So extended means it's laying down filament. Retraction means it's getting ready to make a head move. And again, gives you a lot of information about the print. One of the values of this, from my perspective, is that it allows you to leave the room, right? So I can be in my living room, kind of checking out my print. I don't have to be here in the room if I'm concerned about it. You also have controls that allow you to stop the print, move the hot end around to get the hot end out of the way if you need to. And then the final kind of fun piece of this is that you can record time lapses of the print. So you can kind of see the print as it proceeded faster than real time. So I don't know if I'm going to be able to get that to move here. Yeah, it may not happen. So Octoprint again is a nice utility that that again is just, it's not a need to have, but it's a nice to have as part of your complement. So any questions about printing?
Yeah, I have a question on the Octo. Like, I would have thought the printers would have had that utility built into them themselves, or do they? And this is just maybe a little better, or
It depends. Yeah, this is another. It depends on the printer, right? So Prusa doesn't. Prusa actually has a display that you can examine that'll show you kind of where the print is in rough terms, but really no ability to monitor outside the use of this kind of utility that I'm aware of. Other printers like the Dremel printer have a built-in capability, much like Octoprint, that would give you all of that utility without having to use a device like this. But you know, this is very simple to set up, adds a ton of utility. So,
thank you.
Just a comment on slicing and design. When you're designing your part, especially if you're doing like a box or a big enclosure or something like that, there's two things you can do to make life easier. First is you can sort of give some thought to which part of your part is going to lie flat on the bed. And
yeah. Yep.
Yeah, and if you give that some thought, you can eliminate a lot of the supports, and you can make it stronger just by thinking in three-dimensional terms. Once you're designing a part, how is it going to actually lie on the bed? And so, for example, that little thing you've been showing, Jim, with the U-shape thing, you could actually flip that to print sideways lying on the bed and eliminate the need for all kinds of supports. Right, but you can't do that here because you've got the bottom level.
Right, exactly.
So what you can do for there is the second idea is you can actually get rid of the bottom level, print the vertical level without supports, print the bottom level separately, and then super glue it together. And with certain kinds of plastics, the super glue works very well. And so those are two things you can do to sort of make your life a lot easier, but you got to think in three dimensions while you're designing your part. How's it going to lie on the bed? How are you going to fit it all together, and stuff like that?
Yeah, and actually to John's point, and great point, you can use actually tools within the slicer to cause that, right? So if I want to split this part into two pieces for some reason, I can use this little capability within Prusa Slicer to perform the cut, and you can see it lays the part down. Now, you know, doesn't make a lot of sense in this particular part, but definitely makes a lot of sense in some parts, and then you can glue them. And in fact, one of the topics that I thought about talking about with the finishing process is this notion of using acetone to smooth parts, right? So there are certain parts like ABS and ASA that'll work very well with chemicals like acetone. And there are, of course, lots of warnings about using acetone in open air. I've actually used it to smooth some parts, just more as an experiment. It can work very well. It did make my wife very nervous when I was doing it. And it, of course, it does make a lot of smell. You need good air movement and that sort of thing. So again, just don't say I told you, but Google acetone smoothing Prusa, and you'll find the article that Prusa's.
Hey JR, have you tried tetrahydrofuran for gluing PLA?
So I haven't.
I use it all the time. Pretty good. Almost works as good as acetone on ABS.
Interesting. Yeah, I haven't, just because of its carcinogenic properties. But as a former military guy that used to be up in my hands in it, in those sorts of chemicals, I've become a little bit conservative. But yeah. Again, there's a wide variety of chemicals. Those chemicals depend on the type of material that you're using, right? So some materials can be smooth this way. Other material, a really easy way to finish some materials is just to do a resin-like paint around the material itself. You can find that on Amazon. It's like $20, and it really gives a beautiful appearance to a part if you care about that kind of stuff, right? Most of my stuff is meant to be in the shack or kind of outdoors, so I care less about how pretty it is. But again, all those techniques are available and are great ways to kind of improve the quality of the finished part. So with that, Rod, I think we've made it through demo rules and everything.
No massive telecom disconnects. Well done. Well done. Okay, before we end our recording, any last minute questions?
Yeah, just a comment, really. JR, it's Frank. I'm delighted you made this licensed under Creative Commons. I bet it's going to be a best reader. You're not selling it, but a best reader. So job
Cool.
well done.
Thank you very much. And I will make this available in a PDF form for consumption. So Rod, maybe you can help me figure out how to distribute that to folks, but I'm very happy to make that available. So
Again, JR, great presentation. I learned quite a bit. I have a Prusa i3 Mark IIIs. Wonderful machine. Let's talk afterwards. I want to ask you for a little help.
sure, happy to help.
JR, I think especially from your presentation slides, you should try to make that workflow slide. That's the best workflow slide I have seen to date. And I don't know how much time you took putting into it, but it's really good because workflow is, when you're starting off in 3D printing, holy cow, what do I do first? What do I do second? And you did a really good job on that workflow slide. Thanks.
Thank you very much. Yeah, again, that was it didn't take long to make it once I kind of diagrammed it, but I thought it captured well kind of the steps of the process. So I appreciate that.
JR shared that with me last week, and I was impressed with feeling like I was at the mall. I could, the "You Are Here" section as we move through the presentation. So well done. And unfortunately, JR, that has now, the quality of that presentation has now promoted you to a regular contributor. But thank you so much. And with that, I'm going to wind up. Join us again in a couple of weeks for another recording. Thank you so much.
Anyway, now that we're offline, I want to ask JR